Yeah, recording has started. So, good morning once again to all of you. So, in the last class, we have just started our discussion on this different type of standard forms of representing these Boolean functions, right? So, we have seen there are basically two types of forms. One is the mean term, and the other one is if you want to represent a Boolean function in terms of its max term. Right. We have briefly discussed this that main terms means when you express a function in this type of form, right? This type of form, where it is like xy plus this, say, x bar y. Okay, like this, a function is represented. So that means between these two literals, you have an AND operation, and then between these two, right, like this and this, you have an OR operation. So first it is the and then OR operation. Whereas you might also want to represent it in this form. So where say this is a different function, okay, say f1, right? You may want to express it like this. So first you are want to do this OR operation between these two literals, right? It is this x plus y, and then between like there will be like a similar type, this type of maybe say one more literal, one more this y plus z. So here also two literals, and these two literals are connected with each other by related with each other by this OR operation, and finally between these two you have an AND operation, right? So it is basically the OR is first, and then it comes this AND. Right, but here if you see for this case it is this, first it is the AND, right, then it is the OR operation, right?
Sir, we
So let
can open the bracket and do the and first and then or.
yeah, it means no, if you open it then it is not an any standard form. Okay, if you like, if it is finally coming in this type of, if you are writing this form in like this, then it is called the representation in terms of its mean term. If you are putting the terms in terms of this right here, then it is called max terms. Okay, there is a sort of a standard representation. So you have to, it has to be like this. Okay, so suppose if you have some term like suppose xy, and then you have suppose this z into x plus y, then see it is neither matching with this form or nor with this, right? So it is type of then mixed, right? So you cannot do that. Then you have to but if you think about this xz plus this yz, then it's matching with this form, right?
But it
Okay.
is just notation, right? There is nothing related
Just
with the
representation,
max.
representation. Yeah, it is representation. Okay, and we will see that why these representations means why we are using this and why it is important sometimes to know this type of representation, because that will also help us in terms of our circuit implementation. So we'll see that. Okay, so to discuss that, let us start from here. Say we have two literals x and y. Okay, these are the two literals. No, this is not a good straight line. So let me draw it again. So say these two are like x and y, and this is the function f. This is the output basically. So we do not know what is the circuit right now, but we know these are the two inputs, and this is the f is the as of now it is the output. Okay, and this is the inputs, right? So here two inputs means two literals. So we can have like four different combinations: 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1. Right? And say we do not know what is the circuit inside. Say the output is like this. When these two inputs are 0, 0, it is 0. When it is 0, 1, it is 1. When it is 1, 0, it is 1, 0, it is 1. When it is 1, 1, again this output becomes 0. Right. Okay. Then from the things whatever we have learned from here, we will try to represent it in terms of both mean terms as well as max terms. Okay. So let us say like we want to represent it first mean terms. Right. So mean terms. So first we will write here what will be the terms. Like for corresponding to x00, how should we represent this x00 in terms of mean terms? Okay. And generally, there is one type of notation on which is called this designation. That is not so important, but just for our formality, we like. like designation, huh? How it has been represented. Now we will also try to write here in terms of this max terms, huh? Max terms. Here also we'll write the same terms and designation. Fine. Okay. So let us see that. So this when we're writing in terms of these mean terms, so for 0, 0, right? 0, 0, it's basically in terms of this mean term, it is represented in this way. XY. Just a minute. I should have write it in within this. So this x0 and y0, right? So 0 means representation is this x bar, and y also 0, representation is y bar. So 0, 1, it is x bar, y. Then 1, 0, it is x, y bar. 1, 1, it is x, y, right? And we know that, right? When we are writing like this x bar, right, generally we represent, but then that means basically that 0 means bar, right? And here also y0, that means y bar. So it is this 0, 0 representation, it is this 0, 1 representation, it is this 1, 0 representation, it is 1, 1 representation, right? And this here, this mean terms are denoted by this small m, okay, this small m, and they are written in this m naught, just to represent it. This is a first mean term, second mean term, like a zeroth mean term, first mean term, second mean term, and the M3. Right, just a notation. Okay, but remember that first one is starting with the 0 term, huh? Okay. Now, if you want to write this in terms of this max terms, huh?
Sir, I don't get how you are writing the terms, sir. Like for the first you wrote x bar, y bar, how, sir?
Okay, so how we are writing this from here, right?
Yes,
Okay.
sir.
So what is this x0? Okay, so if I say like, suppose this xy, okay, what do you understand from this xy?
Intersection.
Intersection means in the Venn diagram you
Multiplication.
are referring to?
Venn diagram, sir. The middle part.
Intersection of what?
X and Y. Like and.
And operation. So that
Yes.
means it is from the Venn diagram. It is, if suppose this is the x territory and this is the y territory,
Yes, sir. The middle
right?
part.
Right. Then this xy basically denotes this region, isn't it?
Yes, sir.
Right. So this is called the Venn diagram.
Hmm.
Okay. Right. You are right. So here, like this representation is in this way for such that like you put these values in mean terms and they will give you 1. Okay, so for example you put here 0, so 0th bar means 1,
1.
0th like y0, 0th bar, which is 1, so
1.
1.1, it is 1,
1.
right? Similarly you put try for the second term, third term, fourth term, like you can see the same thing has been used.
Okay, we have to bring somehow 1 using this xy.
For mean terms, huh? Right.
Sir, but sir,
Mm-hmm.
sir, but the values of f are not one always, right? It is varying 0, 1, 1, 0.
Ha, ha, ha. So we are not right now, do not see at this moment when you're writing this, do not see this output term. Okay, only see these terms like x, y corresponds to in mean terms, it should be x bar, y bar only, because this x bar, y bar for x equal to 0 and y equal to 0, it should give you 0. It should give you 1.
Okay, sir. So we always tend to get 1.
Right. For this, okay, when you're writing these terms. Okay. So whereas in terms of max term, what we do is that for 0, 0, we write here this x plus y. It's a bit different, huh? It is x plus y. And then you also try to correlate what we are using here. Then here 0, 1. So for 0, here it is x. And for y is 1, so it becomes y bar. Okay. So it is 1, 0. It is here, it will be x bar plus it is y. It is 1, 1. It is here will be y bar, x bar plus y bar. right? So have you noticed like what is the difference between these two? When you're writing in max terms, so you put this term, see, it becomes 0. You put this 2 here, this 0, 1 bar, 0, 1, 0, put it here, see 1, 1, become, all terms become 0 here. And it has been denoted in this way, M0, M1, M2, M3. This is just the designation is not that very important, but only remember is that this is the 0 term, first term, second term, third term. Fine. Okay, let's do couple of things, then you will understand it much better way. So for example, let's write this function f in terms of this mean terms. Okay, so this f. So f is what? You see this f is 0, so you should not consider the first combination. F is 1, yeah, f is 1 for this, right? 0, 1 combination. So when the combination is 0, 1, so take this term. So the term is x bar y. So it is x bar y. Then again see the next term. Next term is also 1. So consider this 0, 1, 0. For 1, 0, the main term is x y bar. So it is become plus because it's a main term representation. Right? See the third term. Third term is 1, 1. So it is 0. We should not consider this term. Right? So basically the function, okay, if you want to write from this truth table, from this part of the truth table, right? Then the function f is like this. Right? The function f can be represented in this fashion. Have you understood this part? Like only this part. How I am writing this function?
Yes, sir.
Okay. Huh.
Sir, in the max term, sir, in the very first term, you have written x plus y.
Uh-huh.
Sir, can you please explain it, sir, how x plus y comes?
How x plus y comes? Okay. So
Yes.
here the terms will be such that you put the for each literals you put the values. Okay. This term becomes 0. You see that? Here it is 0. Here it is 0, 0. This term becomes 0. Here it is like you put here 0 plus 0 or 0, 0. 0, here it is x0, y1. You put a similar thing like whatever we are doing from here. I think just give me 1 or 2 minutes more, it will be much more clear to you. Okay. So it is basically here you
Okay.
write the terms in that. So if put the relative, put the corresponding values of x and y, you will should get here 0, like for individual terms. So have you understood like how we are getting this f in terms of mean terms? Right. So this is also written in terms of like in this. Okay. This is 1, 2, and here summation of 1, 2. 1, 2 means this m1, m2. So because for these two only f value is here 1. Okay. Right. So this is another notation. Okay, what we use for this mean terms. And here you can see we are using this summation, right? So we call them as sum of mean terms. So this is sum of mean terms, right? Because it is a summation of all these mean terms. Okay. Now here's the one interesting thing. The interesting thing is that suppose now you want to find what is f dash, right? Or let us we always use the same notation. We are using this notation f bar, right? So how we will find f bar? We know that if you want to find f bar, just take the like this is basically this f bar, right? Now we know how to split this because from this De Morgan's theorem, right? So use that. So it become x dot y, then again bar. This there was an right. It will become like this, and this plus become dot means or operation become and operation. Then x y bar this right. Now again split with this one using De Morgan's right. So they can become x bar whole bar. This dot will become now plus y bar. Then this was there was a dot, so this is basically this one. Then split this second term. It is x bar plus y bar whole bar. So it is x bar again, then bar. Basically, like suppose x is equal to 1, then x bar becomes 0, then it again 0th bar would become 1. So that means x bar again bar would become x. Right? So you see that this f dash, that is the inverse of this function, can be represented in this fashion. Right? Let us now do a quick multiplication of this term. So we will do a quick multiplication. So x dot x bar, x y, x bar y bar, y bar. You know that x dot x bar becomes 0, right? This is 0, this is 0 from the basic postulates. So this f bar can be written in this way, right? Now, if you notice where these terms are in this min terms, so again, this f dash we have represented in min terms, right? Or sum of min terms, right? So here you see how this, where these terms are. This xy term is here, right? This one is x term. Where is this x bar y bar term? X bar y bar term is here, right? So that means f bar is the summation of m0, that is 0, comma 3. So now notice one thing here from this, that here f is equal to summation of 1 comma 2, right? And see what is this f bar, right? So if you have f is f1 1 comma 2, then the f bar would be the remaining terms, okay, in this truth table, right? Here 1 and 2. So here is this, it is from 0 to 3. So 1 and 2 is been taken by this f. So this f bar would be equal to this, the remaining term, that is the 0 and 3. Is that clear to you? Is this clear to you, this part?
Yes, sir.
Okay. Now see here one more interesting thing. That is, yeah. So let us take from here. Right. So here this f dash, we have seen how f dash can be written in this form. Right? Okay. Now this is f dash, right? And you see it is represented in which form? It is represented in terms of this max term form, because it is, you see it is the max term, right? It is this the OR operation first and then the AND operation between them, right? And for this max term, this term is which one? See from here, this is x plus y bar, that is this term, and this is this term, right? So it is f bar. F bar is x plus y plus this and this. So basically they are a capital M1, capital M2, and they have a product in between, right? So this type of representation is called the product of max terms. Product of max terms, right? And from here, from this, you can see we can write it from this 1 comma 2, right? Have you understood this part? So it can be okay. This here, this is a notation. This is a summation notation, and this is the product notation. So that's what is the product of this max term, and this is the summation of this min terms. So the representation is this one. So now try to distinguish between these two. If when you are writing in terms of this sum of min terms, it is summation of 1 comma 2. But here what we are writing is this f bar, right? Means the inverse function. Inverse function, when represented in terms of product of max term, it is the same thing, right? Pi of 1 comma 2. Same thing means the same, this same, this, like if you say this first term, second term, third term, so it is the second term and third term, right? Means 1 and 2. These terms, like the terms are the same. So have you understood this part? Like where from to start means if you have given anything, any function in terms of mean terms, how can you get its inverse function? And at the same time, from this mean terms, how can you get its max term? And what is the relation? Okay, still we have not got actually what is f, because whatever we have now found is this f bar, right? Means the inverse function of this f, right? Okay, let's say from here we have to find what is this f in terms of product of max term. Then what you will do? Any guess, suggestion?
Sir, F bar of bar.
F bar of bar, okay. And can you tell me, like you are right, but can you tell me what will be the function?
So pi of 0, 3.
Right, very good. So you have seen that, right? Because we have started from here that if this f is, when you are doing in sum of mean terms, it is this 1, 0, then we have seen this f bar is this the 0, 3, the remaining terms, right? So same thing will also apply here. If this f bar is this pi of 1, 2, then f bar of bar, right? That means equal to f, right? That would be equal to this pi of 0, 3. That means if you want to, okay, that means if you want to write it in terms of, this way, then it would be 0 term, that is x plus y. This is x plus y, and this term, right? It is x bar plus y bar. Yes, is it clear to you now? Are you getting that missing link?
Yes, sir.
Okay. So then
Sir,
can we
which link,
proceed?
sir?
No, that some part was missing, right, for you in understanding. So have you got that part now?
Yes, sir. Yes, sir.
Okay. Okay. So I hope this max term, mean terms, this is a simple representation and you understood. And if one representation is given, from that, how you can find the other representation, right? And how you can, if this f is given, how you will find f bar in both max term as well as in terms of mean terms, right? That is pretty easy. If you have the truth table, you can find it very easily. But remember, for that, you have means the function has to be represented in this form only. Means, okay, what do we mean by in this form only, right? Now that is the important thing. See here, how many variables? Two variables, right? Or two literals, x and y, right? So you see this term here, right? For this is the sum of mean terms, right? In sum of mean terms, for individual terms, see how many variables, like both x and y are present. Here also both x and y are present, right? If you see if you see this notation, product of max term, here also f is equal to x plus y. So for this term, both x and y are present. Here also both x and y are present, right? Now suppose if in some cases the function, say the function f1 is something like this, x into then say a x bar plus y bar, right? So this is not an standard standard sum of product representation, right? Because from here you cannot directly find what will be this f1 bar. You cannot directly find it, right? But the function, if the function is given represented in this form only, where like for both as there are two variables, both the variables are present. So for this type of representation, you can easily say, okay, if this f is this, so this f bar would be equal to x plus y bar and this x bar plus y, because this term means 0, and like sorry, yeah, this term means 0, because right, and this term is this 3, so the its inverse would be 1, 2, right? So you take the 1, this is 1 and this is 2. That's why you can easily write this function. Okay, so here one thing I want to mention here, just for your information, that this particular form, Okay, this particular form means where you can see both the variables, right? Here also both the variables. These forms are called the canonical forms. Okay. These are called the canonical forms. Means all variables are present. Like whatever variables are there, all the variables are present in every term. Then these are called the canonical forms, or sometimes it is also called the standard form. Standard forms. Okay, so standard form in product of mean and product of max term, I think you have understood. Now we will do couple of examples from where you will understand it much better.
Sir,
Huh.
sir, we can say that for the max terms, we would product the zero means the terms zero as the output, and for the min terms, we have to add the terms which are getting one as the output.
I think the similar thing is also coming right from here, right? Isn't it? Like for here, the product of mean terms you have taken one, right?
Yes, sir.
But
For
right,
max
but
terms also, sir.
right.
We can take no, sir. Like it would be a fact.
Could you please repeat which one would be the
Like
fact?
we could follow this thing always, sir.
No, could you please
I'm
repeat
asking.
what we can follow?
Sir, for the max terms, we have to make the product of the zero, the terms which are having zero as the output.
Mm-hmm.
And for the min terms, we have to add the terms which are having one as the output.
Yeah, if for the regular function, if it is the inverse function, then the things will be different, na?
Okay.
Right?
Sir, what is canonical form?
This is standard representation. Suppose if you have this comma x, okay. See, maybe from example only we will understand it in a better way. Okay, so let us do an example, two examples in fact, and then we understand. Say, the function is a b plus a b by. Okay, but here it is given that f is a function of a b c. So, right, means three variables are present, right? It is a b and c, right? But if this f can be represented in this fashion, right, then you are being asked to express it in, it would be sum of product, SOP form. How can you do it? So there are three variables a, b, c, but here in this function you can see you have only two variables, right? But so this is obviously this is not an canonical form. Okay, expressed in SOP or this canonical form or standard canonical form. Okay. So see here, this f is equal to ab plus
So
a. Huh.
should we say that product of sum or sum of product? Because in canonical
Yes, sir,
forms
it
we
is product of sum.
In canonical form,
We are
we
doing product of sum.
product of sum. No, this is also canonical form, na? Like, okay, I think I have, should I have not mentioned? Okay. So here, okay. So this canonical form is this is obviously in canonical form. This is also in canonical form. And this is also an canonical form. This one. Okay. So any standard representation in sum of product or product of sum. Okay, but it has to be the standard representation. Those representations are called the canonical forms.
That
Then
Okay.
the question you mentioned express it in the canonical form, but it is already in the canonical form, right?
It's
AB
not in
plus
the canonical form because see, in canonical form, they are see this for this there are only two variables, na a and b. C is missing, right?
yes. Okay.
Do you understand? So all three variables has to be there. Then it is the canonical form, huh? So
Okay.
here this f is equal to this ab. So we have to introduce c terms in like here both places, right? So probably what we can do, we know that here we can write 1, right? We can so we can make an AND of 1, so that becomes AB only. So this 1 can be written as C plus C bar, right? Similarly, this can be written as C plus C bar, right? We can also take here and 1, and this 1 can be written as C plus C bar. So it is simple only. So it is this ABC bar, AB bar C, A, B bar, C bar, right? So you can see here there are 4 terms, right? 4 terms. So from here we have to find the, actually now this is actually the SOP, standard, sum of standard SOP form. You see that, because here this function like this AND operation and then OR operation, and for each term, like for each this here 3 variables are present, all 3 variables are present, right? And see how easy it is from here to find it, time of this product of sum. It is, what is this 111? What is this 111? So what is this ABC number?
0.
Why?
7.
Sorry, sir.
7.
You see from here, this when it is like XY, it is 1 1. So that means all terms has to be 1, right? Right. So it is how much? 1 1 1 means 7. Okay. What is the next this term? So it is 7. Let me write it small. 7. This time this is 1 1 0. So this is 6, isn't it?
Yes, sir.
This is 5, isn't it?
5.
Yes.
This is
4.
this is 4. Okay. So we will write it from this order. We will follow the order. So this function, when represented in this SOP, it would be this way, right? Now, why we have to need
Sir?
this representation? Just please give me a minute, 1 minute. Huh? Then, if you have to find this F bar, what you have to do? Then F bar would be equal to this 0, 1, 2, 3. Let's see the remaining 4 terms are here. So the remaining terms would become F bar. So if we have expressed this function in this SOP form, right, then it would be very easy to find its inverse function. Yes, please.
Yes, sir. My doubt got cleared, sir.
Okay.
Sir,
Huh.
here we are anyway writing the terms, right? 4, 5, 6, 7. So why is what is the necessity for sigma? We can directly like 4 plus 5 plus 6 plus 7.
4
In a
plus, this is just notation, sigma this sigma indicates means the terms will be like, this, there will be addition, this OR operation between these terms. This is the fourth, between this fourth and between fifth, there will be, and this plus sign means the OR operation.
Okay.
Okay. So is this clear, right? So what is this standard canonical form? So standard canonical form can be SOP, means sum of product, or it may be product of sum, right? It can be both. So it is sum of product. Okay. So next example is this. Example 2 is, say this F is X of, it is going down. F is equal to XY plus X bar Z. And here F, again is a function of given this X, Y, and Z. And obviously it is from here, it is also understood that this, there are like X, Y, and Z. These are like 3 variables. Okay, I think before I go to this, I should mention one more thing. Okay, so you see from here, so this is the function, right? So we have started from here, we have introduced C and finally got this is SOP form, right? But now see, in this SOP, you can take these things common, right? You can take these things common, and you will finally, like, if you, now we have gone in this path, follow this path. If you follow the reverse path, suppose if you have given this one, the last one SOP, then you could have followed the other way, right, to make this function simplified, right? So obviously you can, and this type of manipulation we have already done, right? So during our Boolean function, like different postulates when we have studied, right? This type of thing we have already done, right? So it is just the inverse process, okay, to minimize it. But for this representation, your number of gates required would be less, right? But from here, if you have to say like what is the inverse function, okay, it would be certainly at that moment would be difficult for you, because here you can obviously do, you can take in function, but if it's suppose a lengthy function, okay, then it would might be difficult for you. Right? So for that, what you can do, you can just represent it in this f, and in the standard form, and then from here you can easily find it like from this here. And also we will see like in this type of representation will also help us when we implement some function with either NAND gate or NOR gate. Okay, this type of representation will help us. Okay, so here this is the function, and here we have been asked to represent it in terms of I think POS, express in POS, product of sum. Okay, it is, let me write also the standard POS form. Okay, product of sum form. So can anyone help me in this? How to go ahead?
Sir, first we can calculate the SOP and then we can convert it.
First, you want to calculate SOP and then you want to convert it. Okay. Yeah, that is possible. Yes. Any other way you could have
Sir, we can
thought?
add z bar and y bar.
Yes, means that's what your friend has also suggested, I guess. Yeah, that is possible. I think what you are trying to say, that we can add here this z bar, and here like here this y bar. Then from here, what you will
No
get?
sir, no sir.
Then
I'm saying xy plus x bar z plus x bar.
you want to split this?
No, no. I'm adding a term.
You are adding a term. Okay, let me write it. Yeah, please tell.
So xy
Xy
plus x bar z
plus x bar z
and plus
plus
x bar.
x bar. Okay, yeah, that's
Yeah,
fine. You can write it. Then
yeah. I mean, I'm not saying it should be x bar only. Like we can write x bar or y bar or
mm-hmm,
z bar and
mm-hmm.
make some
But how
combination.
this will help you?
So we can take something common if possible.
Okay. Okay, probably okay. What about this? Suppose, see, this is the same thing. What we will write? We know that, right? This A plus BC can be written as A plus B, A plus C, right? So similarly, we can probably like consider this as A and this as BC, right? I think for one of you, your microphone is on. So could you please mute your microphone? Whose microphone is on? Okay, so here this f is this function, so it is x y and this x bar, right? And it is xy plus z, right? Okay. Now again, probably we can see here again we can split it using this formula, right? So we are not following at this right now, huh? We are following this one. So here we can again split it. So it is x plus x bar, it is y plus x bar, it is x plus z, it is y plus z, right? So this function anyway, this become 1, no issue in that, right? But for this function, right? This x bar y, we can obviously add this z bar, right? Here z, we can add y bar, and here y plus z, here we can add x bar, right? Now again take this as a, this as like b and c, again type of split. X y, it is z, x bar y plus z bar, x z y, x z y bar, y z x, y z x bar, right? Okay, here I think some terms should be common. For example, I think these two terms I can see they are like the same. Now you know that same x dot x, basically x. So we can remove one of the term. Is there any other thing which is common? I think this term is also common, right? This term is also
Yes, sir.
right. So what we can write from here, x plus y plus z, then this x bar y z, this term, and then x y bar z, and here x bar y z bar. Could you please check, have I done everything correctly?
Yes, sir.
Okay, now if this is correct, then tell me what will be the numbers. This is how much?
7.
This is 7. Again you are doing mistake. This is in max term,
Zero.
First
right?
0,
So it is
0.
0 0 0, so it is 0. This one is 1 0 0,
5.
so 1 0 0
4,
is
4, 4.
4. This term
4.
is
5.
0 1 0.
2.
No, it is
5.
0 1 0, so this is 2.
2. 2.
And the next one is, it is
1,
1
0,
0
1.
1, means 5, isn't it? So it will
Yes,
be
sir.
0 2 4 5, right? Isn't it?
Sir, is there any order in writing those numbers? Should
Just
be
to follow the like form, like like type of increasing order.
like in the previous you mentioned in decreasing.
Is it decreasing? No,
Oh, sorry. Okay.
it is increasing only. Okay, so from here, if I ask you, what will be f bar in SOP? Can you tell me
Sir,
what would be f bar
sigma
in SOP?
0 to
Sir,
5.
this only, sir.
Same thing, right? It's f bar
Yes, sir.
would be equal to this of
0,
0
2, 4,
to
5.
4 5,
5.
right? Okay, so f in SOP,
Sir,
function f,
sigma 1367.
very good, 1 3 6
6 7.
7, right? So now we can understand, like, it is very easy to do, right? Okay, so then we can move to the next part. The next part is quite important, and it is called Carnot map or K map. Now, what do we mean by, or what is the utility of this K map? Right. So, in the last class, we have, I think not last class, last to last class, right? We have seen how to minimize an function using a Boolean algebra, right? We have given some function, then we take something common, right? And make the function as small as possible, isn't it? Now, let me take a very small example. If I can find that example, that would be quite nice. Just give me a minute. I have all these functions with bit bigger variable. Probably I can take it with this x, y. Just a minute, huh? This function is x y bar. This function is 1 1 x y. This function is x bar x bar y. This function is x bar y. Okay. Yeah, hopefully this will work, but let us try this. Okay. Say a function of two variables consisting of two variables is like this, huh? X, y, this way, right? So can you minimize this function? Means, if you want to represent this function or implement this function using gates, you have to now minimize the number of gates. So it means you have to reduce this expression. So can anyone suggest, like, what should I do?
So take y bar x
Sir, we
common
can
in the
take
first
X
two terms.
plus
common from
x bar y.
first two terms.
From first two terms, what should be we take common? X.
X.
Okay. Then it become y bar, right? Okay, very good. What next? So this term is actually 1. So x dot 1 become x plus this. Can you do anything in this for this?
A plus BC. We can
Okay,
apply.
yes, it is a plus bc, right? So it become again this plus this, right? Again this
Sir, but
term.
here,
Huh,
okay, sir. Yes, I got it, sir.
got it? Okay. So see, this function is actually x plus y, right? So from this x plus this, this is the function, right? And this is also the same thing, right? But here we have used the Boolean expression, means a Boolean algebra to minimize this, right? Because we can do it because it is quite easy to understand from here. It's quite simple function. But sometimes these functions are so tricky that it will be very hard to get an minimized expression using the Boolean function. So for that case, what we need is we need the help of this Carnot map. Okay. So and this is actually first proposed by one mathematician like Rich, and then it has been modified by Carnot. Okay, so that's why it is called this Carnot map. Huh? This is the name of the person, this Carnot. So now see okay, let us take the same example, this one only, and see how can we implement this or get this from here to here, the same thing what we have done using the Boolean algebra, same thing we can do it from the Carnot map. So for Carnot map, we have to first notice how many variables are here. So there are two variables, so there will be 4 boxes in the table. Okay, 2 variables means 2 to the power 2. Okay, means 4 boxes. Okay, so we have to write it in this way. So 4 boxes, okay, and then add this. Write the variables. So here it is x and here it is y. Means here we will write the values of x, here we will write the values of y. So y can take this 0, 1 value, x also can take 0, 1 value, right? So basically, then this block indicates 0, 0. So we'll write x is the first, like the first one, right? So x 0, 0. So it is basically the 0, 0. This block corresponds to 0, 1. This block corresponds to 1, 0. This block corresponds to 1, 1. In terms of this then value, if we say the mean terms value, this is m0, this is m1, this is m2, this is m3. Remember, the small m is the mean term. Okay, so it is m0, m1 means basically 0, 1, 2, 3, like this. Okay, and you can also understand from here. So what is this m0? M0 is 0, 0. That means it is x bar, y bar. This block corresponds to. This block corresponds to m1, which is 0, 1. 0, 1 means x bar, y. This block corresponds to 1, 0. That means it is x, y bar. This block corresponds to 1, 1. That means it is x, y. Fine? Right. Now, let us use this concept and put the values for this function in this Carnot map. So it is x, it is y, 0, 1, 0, 1, right? So it is x, y bar. So where is this x, y bar? X, y bar, right? X, y bar. X, y bar is this. So put 1 here because this gives a 1, right? So it is 1. Then x, y. X, y is here. Write 1 here. Means whichever terms are present, write 1 in that places. X bar, y. X bar, y. X bar, y. So here. Right here 1. Right? So 3 ones we have written. Now we have to make a group. Now for Carnot map, the grouping technique is like this. You can, you have to like do a grouping for either for 2 or 4 or for 8 or for 16. Means it should be 2 to the power. Okay. So here and while grouping, this ones has to be side by side. So here you can see these two ones are side by side. So we can do a grouping of this. Right? And for this, what we can see is that here for this group, x value is fixed. X value is fixed at 1. Y value is changing. Means y is for both y equal to 0. This means this group consists for both means this group is in this group y value can take either 0 or y can take either 0 or 1, right? But x value is constant. So this group, this particular group gives you only x. Okay. Then you can see we can also do another grouping for this, right? It is this 1, 1, right? And here, if you notice, here x values are variable. So x values are gone. Y value is constant at y equal to 1. So this will give you y, right? And we have also already mentioned like here this m0, m1, m2, m3 terms, they are basically mean terms. So basically what you will be getting is the sum of the product or sum of mean terms. So it's a sum of mean terms. So final expression from this, what you will get is this x plus y. Okay, see the same thing what we have done from using this Boolean algebra. The same thing we have done here using this Carnot map. So is this part clear? The basic part. Then we will take 3 variable Carnot map, 4 value. So we'll do a couple of more examples. Is this 2 variable is clear to you?
Yes, sir.
Okay.
Yes,
So
sir.
then let us go for 3 variable Carnot map.
And sir, like if we don't get any full one row, then full one row or column, then like for x
Then
10
we have to take. Okay. Suppose okay. Okay, here it will be difficult, right? Because here anywhere you have a one, you can make a group, right? Maybe in the next example, I will show you that.
yes sir, no problem.
Okay. So here the function is given like this: x bar, y, z, x, y bar, z bar, x, y, z, x, y, z bar. Right. So minimize this function using Carnot map. Obviously, you can see here there are 3 variables x, y, and z. So for 3 variables, Carnot map we should put it like this. So how many blocks would be there?
8.
8.
Right. Right. Here variables x and here it would become y, z. So x as similar, it would be 0, 1. For y, we have to be a bit careful. Why we are putting it here like yz value? So yz values can vary from like 0, 0, 0, 1, 1, 0, 1, 1, right? There are 2 variables, right? Y can take 0, 0 and 1. Z can take also 0 and 1. So based on that, we can write 0, 0 from like that, right? 2 variables 0, 0, 0, 1, 1, 0, 1, 1. This is the yz can take this board values, right? But here, while you are putting it in Carnot map, you have to be careful that you have only one variable that is changing between 2 consecutive blocks. For example, see here, if we are considering this block 0, 0 to 0, 1, only this the Z is changing, right? Right. So only one bit is changing. Next, see that this one here, one from this to this, you see both Y and Z, they are changing, right? But if you see from this two, here only Z is changing. So this is not allowed. Where both the variables will change, that is not allowed. Only one variable can change. So for that, what we can write, we can do the sequence a little bit different. We can write it 0, 0, then we can write 0, 1, then we can write 1, 1, then we can write 1, 0, right? So see here, then what we are getting, from here to here, only one variable change, from here to here, one variable, from here to here also one variable. So you have to be careful while writing these numbers in the Karnaugh map, because then only you can make a group between these two consecutive blocks. Otherwise, you cannot, if you are not writing in this fashion. So here, these things has been changed, the numbering. So numbering is like here 0, 0, 0. That means it is basically M0. This is 0, 0, 1. So this is M1. This is 0, 1, 1. So this becomes M3. This become M2. This become M4. This become M5. This become M6. So this become M7. Right? So remember the numbering here. Numbering has got changed. 0, 1, 2, 3, 4, 5, 6, 7. Right? So 0, 1, 2, 3. Not this one is 2. Right? So the numbering has changed. Now follow this same technique here and see, can we minimize this using this Karnaugh map? X, Y, Z, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Right? Let's see that. Let's put the numbers. Here it is X bar, Y, Z. X bar, Y, Z means it is 0, 1, 1. So this is basically 3. So where is this 3? 3 is here. Keep 1 here. The next term is X, Y bar, Z bar. It is 1, 0, 0. 1, 0, 0 is this 4. 4 is here. Where is 4? 4 is here. Right? X, Y, Z. Obviously, this is 7. So where is 7? 7 is here. What about this? X, Y, Z bar. X, Y, Z bar means 1, 1, 0. So 1, 1, 0 means basically 6. So where is 6 here? 6 is here. So 6 is here. Now, how can you make now the grouping, right? And always remember that you should always try to maximize the group. Suppose in one case you can make a grouping by using 2 ones, right? But if you do little bit modification and if you can make a grouping of 4 ones, then you should make grouping of 4, right? Because the bigger the group, the minimized would be the expression, right? So let us see that how we can proceed for this. Okay. So here how we can do the grouping. Here it is 2 ones side by side. So obviously we can do a grouping for this, right? And for this, what would be the expression? See here, x value is constant. X value is constant at 1. So it becomes definitely x. And between y, z value, right? Y, see the z value is changing. So z value is ignored. Only y value is constant at 1. So it becomes xy. Right? Let's take a group of this. So when you are taking a group of these two, right? Then this is here x value is changing. So x value is not there. Yz value is constant at 1, 1. So it becomes only yz. Can we make any other group here?
Sir, can we make a group like the 100 and 110?
100 and 110. Yes, actually that is very good. Actually, this Karnaugh map is foldable. Means you can actually fold it like this. Mean you can touch this corner and this corner. Like a page. You can think of this is a sheet. So you can fold this sheet to this. So that way you can make a group of this. So Carnot map is foldable, means you can fold it in this fashion, means you understand, right? Means you can take a fold it like this, or if required, in some cases you can fold also in this way. Okay, so that we can make a grouping of this as well. So if you do a grouping of this, so here you can see x value is constant at 1. So let us write this x. And between y, z, y value is changing, z value is constant at 0. So it becomes x, z, right? So the final function from this, from this would come as xy plus yz plus xz bar. So this is the minimized
Sir,
expression that we are getting from, yes.
sir, the XY group is redundant.
This xy group is redundant here. Okay,
Yes, sir.
can you please explain why?
Sir, because both of the element in group XY are in other groups. So if
Both
even
of
if we
these, yes, both of these, very good. Both of these here in the, they are in the other group. So how should we have done this? Because, right, you're very right. I am happy that you have noticed it. See here, this one, right, we have taken, we could have taken it like this, covering all the ones. We could have taken it like this: x, y, z, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Then we have this 1, 1, 1, 1. Right? We could have taken this. That way we have covered this, these two ones. We could have taken this. Right? You know why to take again one more group? Because this one is already been covered within this. This one is already covered within this group. So why to take one more group? So you are very right. So if you are doing it from here, then see what you will be getting. You are getting here this yz for this, and for this you will be getting xz. So this part is redundant, right? So one thing you should be able to careful, that you should consider all the ones that is present in this Carnot map, right? And you should always try to make the group as big as possible. I think we should stop here today, okay, because the time is already over. So we'll start from here in the next class, and we'll do a couple of more examples of using Carnot map. Okay, okay then. Thank you very much.
Thank you,
Sir?
sir.
Thank you, sir.
Ha.
Sir,
Thank you,
why
sir.
did you put 1 0 after 1 1? Like we could also put this 1 0 after 0 comma 0, sir.
Which one you were referring to? Could you please point it out?
Sir, like the displacement of 1 1 and 1 0, sir.
Displacement of this one, 0, 0, 0, 1,
Yes,
this
sir.
one.
Yes, sir. Yes, sir.
Okay.
This order, sir.
Okay, what do you want to, how do you want to change it?
Sir, I want to place 1 0 after 0 0. Like why I can't do this, sir?
Okay, 1 minute. So it is 0, 0, then
1 0.
0, 0, 1, 0,
Then 1 1 and then 0 1.
then 1, 1, then
0
1,
1 0 1.
0, 1.
Yes, sir.
Okay.
Sir,
So
like why
here,
this is wrong, sir?
1 minute. I have not told that this is wrong.
Acha.
Yeah, here also this condition is valid, right? You have only
Yes,
one,
sir.
one change, like only change of only one,
Yes, sir.
only one variable, right?
Yes,
Yes,
sir.
but here what will be your sequence? It would become 0. Then considering the x value as 0, so this is basically 0. So this would become how much?
2,
2. Then this is
3,
3.
and
Then
this
this
is
is
1.
1. Yeah, I think could you please try using this one as well?
Sure,
The
sir.
same
I'll be
thing,
trying.
using this, and check whether you are getting. I think you should be able to get the come up with the same thing, right? But only thing that you might face difficulty is that you have to remember here it is 0, 1, then 2, 3.
Okay, sir.
Like here it is like 0, 1. We remember 2, 3 like this. So here you have to remember this 0, then here 1. It is then 2. It is 3.
Okay, sir.
Okay, but please do it. What is your name?
Dhruv, sir.
Dhruv. So Dhruv will please do it, and maybe
Yes,
you can
sir.
mail. Okay, after doing this.
Yes, sir.
Okay, for the same thing, same example, do this and check whether you are getting it using the same answer or not.
Okay, sir.
Okay, so when can you mail me today?
Sir, actually we have a test today, sir. So I'll mail
Okay.
you mostly tomorrow, sir.
Okay, tomorrow. Fine.
Okay, sir. Yes.
Okay, then. Thank you. So I think
So,
the class.
Thank you, sir.
so instead of taking X and YZ as a group, we could have also taken X, Y, and Z as a group, right? Although it
Uh,
might be a bit confusing, but it's permissible, right?
which one? Which one is the grouping?
So in the table, instead of
Hmm.
splitting it as
Uh-huh.
X and YZ, we could have
Uh-huh.
taken it as X, Y, and Z also, right?
Means you want to okay. Means you want to take it like in this way. It will be like this, right? Are you
Yes,
saying
sir.
this?
Yes, sir. Yes, sir.
Yeah, it's also possible. It's
It's
also
just that XZ would become would make it a bit confusing.
right, because we are
All right.
more we are more means we
Yeah,
can do
this is
much
more
more better analysis
simple.
if something is in this way, right?
Yes, sir. Yes, sir.
In fact, in the next class, I will show you not only these three variable, we will also do couple of examples for four variables, right? So for four variables, you will see there will be like 16, and here you will see like suppose wx, yz. This type of things are also will be there. So not only this, you could have make five variables. Five variable, then it becomes how many? 36, right? But I will just only show you how to just how this 32-bit or the five variable kernel map looks like, but we will not do much analysis of that. We will try to restrict ourselves within this four variable one. Okay.
Yes, sir. Thank you, sir.
Okay, then. Thank you.